Hello everyone. In this video, I will go over my solution to the problem E named grid XOR taken from today's Codeforces round. This problem is an excellent problem on constructive algorithms, and it uses only one very simple observation which essentially just makes the problem very simple. So in this problem, we are basically given a grid of size n cross n where n is an even integer and aij is the integer in the ith row and the jth column, and it's up to 2 raised to 30 minus 1, and this means that it basically has 31 bits, so it fits inside the integer normal int data type. And we are given the XOR sum of all adjacent cells for each element in the grid. So for each grid ij, we are given the XOR sum of integers which are surrounding them in the four surrounding areas. So if we are considering the position ij, then we take the XOR sum of I minus 1j, ij minus 1, ij plus 1, and I plus 1j. So these four cells, if we take the XOR sum of them, we are basically given that grid where grid ij is equal to the XOR sum of the four adjacent values. So let's take an example. Let's say we are looking at 13. Then 13 is equal to the XOR sum of these four values in the original grid, and that's the grid which we are given. So this new grid which we are given for each test case contains each element. Each element contains the XOR sum of the four adjacent elements in the original grid, and we need to print the XOR sum of all values in the original grid. And we don't need to actually find the grid because there can be multiple possible grids, and this is where the construction comes into hand. There is actually a very simple construction which just makes the whole problem very simple, but let's just go through the examples for now, and let's try to find a possible grid for each of the examples which satisfies the property that the input XOR sum of ij given in the input is equal to the XOR sum of the four adjacent values in the original grid. Let's try to find a possible grid for each of the examples, and then I'll show you the key observation which makes the problem very simple. So first, let's take the example of a 2 by 2 grid. Let's say that the original grid has four cells A, B, C, D, and let's say that the grid in the input, which is basically the XOR sum grid, it stores the XOR sums of all adjacent values from the original grid. So this is the new XOR sum grid. Basically, for the first cell 0, 0 is going to be the XOR sum of the four adjacent cells. There are only two adjacent cells over here. The two above, the one above and one to the left does not exist. That's why the XOR sum will be B XOR C. For the next cell, it's A XOR D, because the adjacent cells are A and D. For the next cell, A and D are the adjacent cells, so it's A XOR D. And for the last cell, B XOR C will be the value in the input. So this is actually the input which we are given. And from this input, we actually need to go back. So there are actually multiple possible ways to go back, but let's not worry about that right now. Let's just worry about the final answer. So in this case, it's clear that the final answer will be the XOR sum of A, B, C, and D, because that's what they asked us to find. They asked us to find A XOR B, XOR C, XOR D, and that's actually equal to the XOR sum of the two adjacent cells. Because if you take A XOR D and if you XOR that with B XOR C, you get A XOR B XOR Z XOR D. So the final answer is actually given by the input grid of 0 of 0 XORed with the input grid of 0 of 1, because as I just mentioned, the input grid of 0 will give us B XOR C, and the input grid of 0 of 1 will give us A XOR D. So we know that when n is equal to 2, we can just simply print the XOR sum of the first two values in the grid from the input, and that's going to be the final answer for n is equal to 2. For larger n, however, it becomes harder to actually make the grid and to actually calculate these values. That's why I'll show you one observation. But first, you can see in the example that 1 XOR 5 is equal to 4, and that's the correct value. And you can see one possible original grid. Now I would like to propose a construction for the original grid which will actually work for all values of n, and will actually make the problem very simple. So let's continue to look at the 2 cross 2 grid, but let's try to simplify the values. So let's say without loss of generality, or let's just say that the first two values in the grid are 0 and 0. Let's say that holds. Then how can we basically choose the next two values efficiently so that the input grid satisfies the condition? So the key idea for choosing the next two values is that if B is XOR C, so let's say that the XOR sum of 0 0 is B XOR C. That's the XOR sum for the first index, and this is the original grid. So this is a simpler version of the original grid, and this is actually the key observation. I will actually informally prove with the help of examples that we can always choose the first rows to be 0. We don't need to set them to be A and B. We can set both A and B to be equal to 0. And the reason why we can set both A and B equal to 0 is because if you set A and B to be equal to 0, then you will realize that the values which you store in the grid are actually, so the XOR sum grid actually gets transformed to something like B is equal to 0 and A is equal to 0. That's why in the case for 2 by 2 grid, you will get C, D, A and C. I mean A is equal to 0, so you get C, D and C. And basically this is the XOR sum grid. So that's why the original grid can be recovered by easily using the fact that the XOR sum for 0 0 is given by the XOR sum of the two adjacent values. So that's why it's going to be the XOR sum of 0 and this value. So that's why we set the value to be equal to C, so that the XOR sum becomes equal to C. And in the next value, so if you consider the number D, the value D comes from the fact that it's the XOR sum of these two elements from the original grid. So that's why we can set this value to be equal to D. So the final answer for the grid would then become equal to C XOR D, where C and D are from the original grid, because we assumed A and B are equal to 0. And you can verify that this actually works if you take this array and if you calculate the XOR sum for all of the adjacent elements. You will get that for the XOR sum grid, you will get the grid to be of the form: the first element is C, because 0 XOR C is C, then the second element is a D, then the next element is a D, and the next element is a C. And if you realize, this follows the exact same pattern of this original grid. Why? Because the first element and the fourth element are equal. So these two elements C and C are equal. Even in the original grid, original XOR sum grid, B XOR C and B XOR C are equal. And similarly, D and D are equal because A XOR D and A XOR D are equal. And in general, for any grid, you could take C, D, D, C, you could take it in this form, and you could get that the original grid is actually this. And because the original grid is actually this, you have retrieved the whole original grid by setting the first row to be zeros, and you realize that C XOR D is the final answer, which is the XOR sum of the remaining rows. And you can even verify that this works for any 2 by 2 grid. And now let's try to understand from the remaining two examples why it also works on 4 by 4 grids and larger grids. So let's consider a 4 by 4 and larger grid. The key idea is that once you fix the zeros over here, all the remaining elements get fixed. And the reason why all the remaining elements gets fixed is because we know that if this is the original array and the next array is the XOR sum array, then for a given XOR sum, so let's say that we are considering XOR sum of I of j. So we know that XOR sum of I of j is equal to the original grid g of I minus 1 of j XORed with g of I plus 1 of j. So these are the two adjacent elements above and below, and then the two adjacent elements to the left and to the right are I of j minus 1 and I of j plus 1. So this is the XOR sum of I of j. This is the input grid, and the grid which we need to find out, which is given by the original grid, will actually be equal to, so if you want to find the value of a particular element, so let's say you want to find g of I plus 1 j, then the key idea is that g of I plus 1 j is equal to if you take the XOR sum on both sides, so if you XOR both sides with the remaining elements, so let's just basically isolate this element. Let's isolate this element, and the remaining elements, these remaining three elements, will get XOR summed. So we take the XOR sum of the remaining three elements on the both sides, and since you know that any number XORed with itself is equal to 0, that's why if you take the XOR sum of the same number on both sides, you will get that the left hand side is XOR sum of I of j XORed with g of I minus 1 of j, and that is XORed with g of ij minus 1, and that is further XORed with g of I of j plus 1. So this is the value of g of I plus 1 of j. Now how does this help us? This helps us because once we know what I and j are, and once we have fixed the XOR sum of I of j from the input, we can easily find out what is the XOR sum of the next row. This is why this helps us, because if you visualize this in terms of rows, then we are currently at the ith row where I is equal to 0, and we know all the values of the next row. How do we know all the values of the next row? Because if you increase I by 1, you get the first row. From the 0th row, you go to the first row. And for every column j, you know that just by doing XOR sum of the 0th column of j, XORed with the XOR sum of the previous one, the previous row with j, and the same row and the previous column, and if you XOR that with the same row and the next column, you are essentially going to get the XOR sum for the next row, I mean the original value in the grid for the next row. So in general, if you want to find out all the values in the grid, you can just set the first row to be zeros, and you can repeatedly iterate over all I going from 0 to n minus 2, and for all j going from 0 to n minus 1, and for each value which exists, you can set g of I plus 1 j to be equal to this quantity which is given on the right hand side. And this works because we know that this is a possible construction. Like this construction always works. You saw that in the 2 by 2 case, and you should verify that with the examples for the next two cases, and it actually works. So you should spend a few minutes doing the examples and by setting the zeros in the first row, and you will realize that this recurrence holds. And this recurrence, or basically this you could call it a DP recurrence or something, is actually what ensures that XOR sum of I of j will always be equal to this quantity. So this holds true for all I going from 0 to n minus 2, and you can also verify that it works out that this holds true for the n minus 1 row also. That is a bit tricky to prove. So just summarizing it in a bit, we know that for all I going from 0 to n minus 2, XOR sum of I of j is equal to the XOR sum of the 4 adjacent values, and that's why we can isolate one value for the next row, and we can get that the XOR sum of the next row of the same column is given by this quantity. So we can iterate over all I going from 0 to n minus 2 and update the XOR sum for the next row using the fact that all the values are initially 0 in the first row. And you know that from the value of XOR sum ij, this condition is going to be met. So the original grid, I mean the inputted grid, this will basically ensure that this ensures that the input grid contains the accurate values of XOR sum of I of j for I going from 0 to n minus 2, because of how we defined the values, because of the math which I just showed you. So we know that for the first n minus 2 rows, we know that XOR sum of I of j is correct. However, for the last row, we are not very sure, but I don't have an exact proof for why this works for even the last row. So you just have to either look in the editorial, or you can post in the comments down below why you think that this will always work for the last row as well. We can see that it very clearly works for up to the n minus 2th row. Why does it work also for the n minus 1th row? And once you realize that, then it becomes very clear that you can just iterate for all I going from 0 to n minus 2, and you can set the values for the next row to be equal to this quantity on the right hand side. And now I'll just show you the code which does the exact same thing. So in the code, I use vi for vector int and vvi for vector int, because we use a 2D vector to store the grids. And for each test case, I take in the value of n, which is the size of the grid, and I store the XOR sum grid and the original grid. The XOR sum grid is from the input and the original grid is what we reconstruct. So initially I take in the values of the XOR sum grid and I set the XOR sum of all elements to be equal to 0, and this is the final answer. Then each time I use the fact that XOR sum of I of g is equal to grid I plus 1g XORed with grid I minus 1g, XORed with grid ij minus 1, XORed with grid ij plus 1, basically the 4 adjacent cells. And then this means that g of I plus 1g is equal to the XOR sum ij XORed with these quantities, these 3 values, gi minus 1j, gij minus 1 and gij plus 1. So that's what exactly we will simulate in the code. So initially val is equal to XOR, or you could just say gi plus 1j is initially equal to XOR sum of ij. If I is greater than or equal to 0, then we set, if I is greater than or equal to 1, then we set gij, we basically set grid ij, we XOR it, grid I plus 1j gets XORed with the previous value, which is grid I minus 1 of j. Then if j is greater than or equal to 1, we do a similar thing, grid I plus 1j gets XORed equal to with grid of ij minus 1. And then the last thing is when j is less than n minus 1. So for this last value to hold, we need j to be less than n minus 1. So if that is met, we take grid ij and I plus 1j and we XOR it with grid ij plus 1. So in this way you can verify we have taken care of all the 3 neighbors of ij, and in that way we have set grid I plus 1j to be equal to this value, and that's why we set grid I plus 1j to be equal to this value, and we take the XOR sum with the current value of grid I plus 1j. So in this way we have accurately maintained what is the values of each grid, and note that I initialize all elements to 0, so that like in the diagram you can see that the first 2 are all zeros. Then each time for all I going from 0 to n minus 2, I perform this operation of setting the values for the next row and the same column. So in this way we can get the accurate values of the grid values. And as I mentioned while explaining the intuition, we basically ensure that the first row is fixed, and we ensure that all the other values are calculated from the first row, and we knew that this will easily work for all I going from 0 to n minus 2, because as per the loop I goes up till n minus 2, and this means that XOR sum ij will get accurately stored for all I going till n minus 2. However, there is some skepticism about what happens for the n minus 1th row, and if you have any ideas about why exactly this works for even the n minus 1th row, you could leave a comment down below. So I hope this helped you understand the intuition behind this problem, and if you have the proof, do leave them in the comments down below, and you can verify this code does get accepted. So I hope you like this problem and my solution.